Welcome you all to this course on diffraction and imaging. Okay. Today what I thought I will try to cover is how to construct different types of crystal structures or lattices. Okay. You might have studied about crystal structures of various materials like FCC, BCC and all. How are these crystal structures really constructed? Is there any rule governing this construction of these lattices? That is what we, if you understand that, okay, then it is easy to construct any type of a crystal structure, or you understand why particular type of a structures only are possible. Okay. That is what we will try to look at it. What is the basic definition of a crystallography? Crystallography is nothing but study of arrangement of atoms in a periodic fashion. It could be an atom, it could be a motif, okay, an asymmetric unit, or it could be a group of atoms which constitutes a molecule. Okay. There are various types of them. This could be in 1 dimension, 2 dimensional, 3 dimension. This you might have studied also. There are periodicity of various dimensions are possible. In fact, 1 or 2 dimensional periodicity, this part of the study is extensively used in fashion technology, especially in textile printing. Then flooring, which is being put, the different types of designs which are created. For all of them, the same crystallography which mathematicians have developed, that is being used, okay, to represent, also to generate different types of, in fact softwares are available with which one can generate. Okay. But one thing which one should always remember is that the crystallography which you study, like different types of crystal structures, they are called as geometrical crystallography. Okay. The reason why it is called as a geometrical crystallography is essentially is that this study tells what all the various types of crystal structures which are possible. It never talks about which type of a crystal structure, which element or a which type of a crystal structure a particular element, okay, or a particular material will take. There are n number of possibilities are there, right. Suppose we take aluminum. We normally find aluminum takes an FCC structure in the solid state. But why does it take why can't it take a BCC structure or a, that cannot be answered from crystallography. Okay. That comes from the energetics of it, okay, that decides. So here what we talk about it is, suppose we take some particular element or a material, if he has to arrange itself in some periodic fashion, and that too having some specific property, then we can tell that these are all the possible types of crystal structures to which this material, if it forms, this type of properties which it will exhibit. Actual energetics will decide which crystal structure it takes. Okay. Let us start with a 1 dimensional one. Just I have taken some pattern. Looking at this pattern, can you tell there is any periodicity in this? What is the sort of periodicity which you see? It is a linear one. So this is the particular type of a motif which gets repeat itself. Okay. When you look at these type of structures, like if I look at your shirt, or I look at Matai's shirt, okay, everything has a periodicity associated with it, correct? There is a pattern which gets repeated itself. All the cloths which we wear, everything has a pattern which needs. This pattern could be an asymmetric pattern, or it could be a symmetric pattern, but this pattern repeats in some periodic fashion. Okay. What are the types of periodicity? Infinite number of patterns we can have, but still they can have only the one type of a periodicity, correct? That is what is we will understand as we go through. This is another type of a pattern. Okay. It is also an asymmetric pattern. Okay. Here it is easy to visualize it because you can see what the motif which is getting repeated, correct? The other pattern you have to, it is not that easy to make out that which is the pattern which is getting repeated, correct? What part of the pattern is getting repeated? You look at this pattern, what do you see? Between the top and the bottom, these two patterns, two are getting repeated, correct? That is also a periodic pattern, 1 dimensional periodicity. But one thing which you can see here is that if you look at the motif which gets repeated, this motif itself also has got some symmetry associated with it. It's a 180-degree rotation is associated with it, correct? So that's why I mentioned that the motif could be an asymmetric motif like the one which is given on the top, or a motif could be like this, but it's all have only a one-dimensional periodicity, correct? And here I am just showing a two-dimensional pattern. Okay. Here also, is there anything common between them, between these two? Both are two-dimensional. Other than that, actually if you look both of them, they have a square type of a lattice which repeats itself. Here also a square which is arranged. Here also it is essentially a pattern which repeats itself. Okay. We are not able to make out this difference because most of the time our brain is confused by the pattern which we see. When we see a pattern, we do not see the periodicity, correct? How we can overcome this? Each of these motif which gets repeated, if we represent it by a point, okay, and then forget about the motif, we can tell that this is the motif which represents, then it gives a better visual appeal and we will be able to recognize the type of symmetry which it has. Okay. This is another pattern which you can see it, but here actually it is a asymmetric motif. Okay. It is only the one which is expanded. Here what I have done is essentially showing the same pattern. Okay. Now I am represented by a dot. This dot represents each motif. Okay. Now if you look at the dot, you can see that there is some particular periodicity with which the dot gets repeated, correct? To this dot, you can put any type of a motif. Then when you put different type of motifs, we say that different types of designs are there. But actually, the periodicity with which gets repeated, it is almost the same. Okay. And another one which I have done it is that I have just shown here axis. Okay. In crystallography, there is a convention which is followed to represent axis. That one should always be quite clear about it. Okay. You might have seen in books the different way in which crystal structures are represented, correct? Most of the time I find that from memory, most of the students try to draw what is drawn in the book. Why is that particular fashion in which the crystal structure is represented? There is some meaning to it, okay? Following some norms which will come when we talk about stereographic projection. But as far as choosing the coordinate system is concerned, that one some convention is followed. The convention essentially is that from top to bottom is where always the x-axis is represented, okay? Then left to right, y-axis, z-axis is normal to the board, okay? This is the representation which is always followed in all books on crystallography. That any book which you read, one should know that this is the convention which is followed, and one has to follow this convention also when drawing figures. Okay. This throughout the lectures, I will be following the same convention. Okay. Normally, you might have seen that whenever we draw crystal structures in 3 dimension, we wanted to give a perspective representation. How do? We generally try to draw, this is x, this is y, this is z, this is how we represent, correct? Essentially, this is a distorted form of this representation. X is always from top to bottom, y is from here, okay? Then the z, when it has to represent, when it is tilted, this will also be coming on the screen. Otherwise, when these two are in the plane of the board, then this has to be normal to it, okay? That is how most of the books, they represent the axis system. Okay. Now you can see that it is essentially only the dots which represent each of the motif. This dot, we call it as a lattice point. Okay. So, it is a mathematical form of convenience with which we are trying to represent different types of motifs which are getting repeated by a point. Okay. And the spacing between the adjacent points, we represent it as the lattice parameter or the periodicity of the lattice, correct? So, this could be a motif, this could be a group of atoms, or it could be a single atom which are residing at the lattice point. All these possibilities are there. So, today most of the class I will be talking only with respect to the lattice, because the lattice is the one which is represents the periodicity with which the pattern is getting repeated. Okay. Generally, if you have to represent this lattice, okay, mathematically how will we do it? Choose a coordinate system. Once a coordinate system has been chosen from point, then this distance, if it is a, okay, the vector r will represent some n1 into a, we can represent it, which will be the vector. Or in many books you will find that r will be represented in u into v. U, v, w will be the directions which are the number of repetitions which are taking place in those directions, x, y and z. That is used to represent the lattice, correct? Is this so far it's clear? Okay. Generally, the lattice point which we assume that it has a 0 dimension and the symmetry is infinite. Okay. That is the one assumption under which we are doing all this generation of this pattern. Okay. We will see the consequence of it if these points have different types of symmetries associated with. If it has an infinite symmetry, okay, a circle we can use to represent a lattice point, correct? It will be a circle. In a 3 dimension, it will be a sphere which has a 0 dimension, correct? That is how we represent the lattice point. So, crystal structure, the way we can construct is that crystal is a real material, correct? The lattice is to represent the unit which gets repeated, we are representing it by a point. So, that lattice plus the motif put on top of them, that represents the crystal structure. Lattice itself has got a periodicity. Similarly, the motif itself also can have sometimes periodicity, sometimes this can have associated with some symmetries also. Lattice also can have symmetry. We will talk about it a little bit later about the symmetry. Okay. So, the combination of the symmetry of the lattice and the symmetry of the pattern which is put at or around each of the lattice point, that puts some restrictions on the number of types of crystal structures which we can have. Okay. Here the motif which we have chosen is an asymmetric motif. Okay. Here if you look at it, the only difference is that both are one dimensional lattice, correct? But the lattice parameter is different in these two cases. That is the only difference between these two lattices. Okay. But the only difference here is that in this case, the motif itself has got some symmetry associated with it, correct? The same thing how I can represent it is that suppose I use a letter P, okay, the other one will be 180-degree rotation, it will be P like this. This will come to later. This is how, if you look at a pattern, this is the way the pattern will be represented. Okay. Is it clear? Okay. So, here motif also has got some symmetry associated with it. That is what it happens in many real systems. Okay. An asymmetric motif, if we look at molecule, okay, that is bromochlorofluoroethene, is one which is an perfect asymmetric crystal, asymmetric molecule. Okay. Whereas when we consider many of the atoms, okay, atoms we assume that they have an infinite symmetry associated with it. Okay. Okay. Now let us look at here what I had just shown is an example of a few periodicities in one dimension, and as well as the how it can be represented with a lattice. Okay. From this one dimensional lattice, okay, there is only one type of a lattice, a periodicity in particular direction, one row. Suppose we have to construct a 2-dimensional lattice. How many types of lattice we can construct? Any idea? 5 types, because you attended the last class. Others? Anybody can justify it? Is it? Not you. Okay. How exactly we can do it is that this is only a pattern which I am showing it. This pattern we can now, the same pattern we can keep it here, but in this direction, if you look at that x direction, it is kept at some angle with respect to x axis, correct, at a particular distance. We repeat it like this, and if we keep it, we generate one type of a pattern, correct. This is a 2-dimensional lattice. Okay. There are many ways in which we can do it. I can do it by putting it just straight down. Okay. That's one way we can do it. And then I can keep this distance as well as the periodicity in this direction the same or different. Then I can generate another type of a lattice. So this puts some restrictions. This we will see how many we can have. Okay. So before going into the detail, we will look at some basic definitions. The lattice. In this 2-dimensional lattice, okay, this is the 2 vectors which normally used to represent the lattice. Okay. They should be non-collinear. Okay. Generally, those having the shortest translation vector which we use it. But that is not the only way it is represented. There is symmetry is the one which is some consideration which comes into the picture, okay, representing the lattice. Okay, here if you look at it, this is A and this is B, okay, translation vector. This is the unit cell. We can have the unit cell in this particular way also. All these unit cells, if you look at it, all of them have only one lattice point per unit cell. Okay. And all of you might have studied, only just I am starting from the beginning and going ahead for the sake of completeness. So this we call it as a primitive lattice. So the first thing is that the lattice unit cell is not unique to any lattice. There is nothing like a unique unit cell which you can choose, any type of a unit cell which we can construct. Then if you look at any lattice point, it has got identical surrounding around it, correct? So that is another property of a lattice, that all lattice points will have identical surrounding. An ideal lattice essentially is infinite in dimension, so that the surface effects can be ignored, because surface is a discontinuity. Okay. Only in real crystals the surface effects have to be considered and the properties are different. But when we consider a lattice, we consider the lattice as an infinite lattice, so that the surface can be ignored. Okay. Then here if you see, we have a lattice which is a different type of a lattice. Okay. This contains 2 atoms per unit cell. This we call it as a non-primitive lattice. Okay. There are many instances like body centered, face centered, all. We use only non-primitive lattices. Okay, we will come to it later. The reason essentially is that generally we use a unit cell which represents the full symmetry of the lattice. So in this case, what we take as a condition is that A and B lattice parameters are not equal. Okay. The angle between them is also not equal to 90 degree. Okay. This lattice is called as an oblique lattice. Okay. In this type of a lattices, we will be representing the vector R to B. Okay. This is the way we will be representing. Any lattice point can be represented where U and V are essentially integers. It could be positive or negative, correct? There can't be fractions. That is the only thing which you should remember. Is this clear? That is exactly what I have told, that we choose a lattice which represents the full symmetry, because immediately from symmetry only we try to identify it. Okay. Why are we looking at these type of 2-dimensional lattices? Either when you study diffraction, when you take electron diffraction pattern, all are two-dimensional patterns, correct? What all types of patterns which we can have, that will become clear when we go through these slides, okay? Then another way in which these lattices can be represented, which we call it as a tiling. Essentially, if we take a unit cell like this, we can keep adjacent unit cells adjacent to each other and do a space filling, correct? So this is one particular shape which does that, and the space filling can be completed, okay? This you might have seen that when people put this rangoli, they put dots, which is essentially in some periodic fashion. Then either the dots are connected or some figures are made around each of the dots to create various types of patterns, right? Okay. That has a lot of science behind it. Okay. Though people do not understand it, but I think the mind it is worked out. That's why they are able to generate various symmetric as well as asymmetric patterns. You see here, this is another way in which from a one-dimensional lattice, we can generate a two-dimension, because each one-dimensional lattice is kept just below the other, okay? And the distance A and B are not equal, okay? So this lattice is called as a rectangular lattice. The other way in which we can do it is that in one lattice is kept here, another is kept here, okay? One-dimensional. In between, at the center of it, you keep the next one. This way, if you try to arrange it, we get a lattice which is called as a C-centered lattice, or if you look at it, because C-centered lattice is a non-primitive lattice, because there is one atom is there at the center, okay? If we see here, this is essentially nothing but a rhombus is the primitive lattice here, okay? Because every lattice will have a primitive lattice. If you take A equals B and the angle becomes 90, then we get a lattice which is a square lattice, right? And if A equals B and the angle becomes 120 degree, okay, we generate hexagonal P lattice, okay, which has a 6-fold symmetry, okay, as well as it has a 3-fold symmetry also associated with it, rotational symmetry associated with it. These are all the only types of two-dimensional periodic lattices which we can have. This we have studied in geometry, all these names, correct? Parallelogram, rhombus, rectangle, triangle, right? Square. So that's all it is. We have never understood, we have never told that why these are there. These are all the only shapes which we can have. And these shapes are all periodic ones. If you take quadrilateral, that's also, but quadrilateral, it's aperiodic, correct? It's not a periodic shape. Any diffraction pattern you get it in 2 dimension, even with X-ray or with the electron beam if you try to generate, the diffraction patterns should have symmetry corresponding to one of these. From those patterns, finally we try to find out what is the type of a crystal structure which the material has got, right? That's what essentially I had shown here. These are all the 5 lattices, okay? And the periodicity which we see here, this is also called as a translational periodicity, not translational symmetry, okay? We talk about symmetry, okay? The first symmetry which we will see in any material, if it is periodic, is translational symmetry. What is symmetry? That question comes is that how do you define a symmetry? Symmetry is something like a type of an invariance. That is an operation which we perform that brings you to a position which is identical to itself, because from the end position and the initial position there is no difference, correct? So in a lattice which is repeating itself, like this, if I shift it from here to here in an infinite lattice, okay, it comes to a position which is identical to itself. So we are not able to make out that we have we have made it undergo a transformation. So this is called as a symmetry. This is called as translational symmetry. Okay. Similarly, we can have another type of symmetries, which are, one is the rotational symmetry, another is reflection symmetry, is also another type of a symmetry. Then inversion is another type of a symmetry which we can have around a point. So in a two-dimensional lattice, if we consider, okay, this, if we take this case itself, we have around this point, okay, if I take an axis perpendicular to it, rotate it by 60 degree, okay, all the atoms will come to a position which is identical to itself, correct? We will not be able to make out that the rotation has been performed. But suppose we are able to identify or tag each of this lattice point, unless we do 60 degree rotation, then only each lattice point will come back to original position. Okay. So this sort of an operation, we call it as a rotational symmetry, correct? Similarly, if I put a plane here, anywhere here, okay, I have a mirror image of each of the side, right? And the lattice positions are now identical to each other. So this is which we call it as a, this has got a reflection symmetry also associated with it, right? But is there any rules governing the symmetry? If I take around any axis, okay, if 360 is divisible by any number n, okay, that is, I had given n equals 9, if I take it, it will be 40 degrees, correct? If I rotate it 9 times a point, I will be able to come back to original position, correct? But as far as around a point, this is possible. But whether, if there is a translational symmetry is associated with a two-dimensional lattice, is it possible to have this sort of a symmetry or not? There are some restrictions are there. Okay, not all rotations are consistent with translational symmetry. Okay, that how many of them we can have is from this slide which one can understand. Here what I have done is that taken a lattice, okay, this is the translational periodicity, okay. I have rotated this by an angle phi here and rotated this by an angle phi this point, and it has come to, assume that come to another lattice point matching with it, okay. Then this distance, if I try to see, since these are two lattice points, it should be some integer times the periodicity, correct? That is, this turns out to be mt, okay. This mt will be equal to this t, okay, plus the rotation, 2 times it has been rotated, 2t cos phi, okay. So this will put a restriction on cos phi should be equal to, okay, m minus 1 by 2, that m can have any value, 0 plus minus 1, and all these values are possible, okay. But what is essentially important is that now this cos phi, if you look at it, this is n by 2 it turns out to be, because m minus n is taken to be n. Then what are the values which we can have? The cos phi can have a value 360 degree one rotation, okay. It cannot exceed that, correct? So if we take that as a criterion, then the values which n can have, which will give rise to, is 180 degree, 120, 90, 60 and 360, okay, or it is 1-fold, 2, 3, 4 and 6-fold rotation. It will natural consequence, it will turn out to be only these are the rotations which are, because here the condition which we have put it is that it is consistent with the translation symmetry. So with translation symmetry, these are all the only 5 types of rotations which are possible. Other rotations are not consistent with it, okay. We can have around it a symmetry like this, any angle, but in a lattice only these 6 types of rotational symmetry only is possible. Okay. Then another is a reflection. Reflection is, and you should remember here that in this also the translational symmetry, this we consider it around an axis, correct? Around one point we are considering all this translational symmetry. Here if you look at it, this is a reflection, correct? That is the right hand and left hand, and our whole body also has got externally, if you look at it, that is a mirror symmetry which is associated with it. And here a linear periodic one dimensional array is being shown. Here if you look, one fact which becomes quite clear is that I can put a mirror on any of this lattice point, okay, it will get reflected. In addition to it, in between the lattice point at the middle also, we can put a mirror. That also gives rise to, okay, the same mirror symmetry. So there are 2 positions of mirror symmetry is there in this lattice, correct? What I had shown here is essentially only with respect to a mirror, but in a lattice when you consider, not only at one particular point, there are some points other than the lattice point also where this sort of symmetry it can exhibit. This is clear? I will come back to all these mathematical things later and talk about it. Then another type of symmetry which happens also is which is called as a glide, like when we walk on the beach sand, okay, that right and left leg, both of them are mirror symmetry of each other. Only thing is that with a periodicity, half of the distance between the legs which we keep it, okay, that half the distance is with which, that is as if like here what is being shown, it is an R, okay. This is the periodicity here, but if I repeat it by half the distance and take a mirror reflection, it will come here. Again move half the distance and take a mirror reflection, it will come to this point, okay. This is how it gets repeated itself, okay. This is around these lattice points we have, but this automatically generates another glide symmetry plane halfway between, okay. Essentially in crystals we can see that because there is a translational periodicity is associated with it, okay, it gives rise to some points also other than the lattice points where some additional symmetry elements can come, okay. That is what the message which I wanted to convey. Here what I had just come back again to the 2D lattice, okay. If you see, this is the primitive P lattice, okay. In this lattice, around the center, okay, if I rotate it by 180 degree, this point will come here, okay, this point will come here, 180 degree rotation is there. Similarly, I can take any point as the center, okay, we will have that twofold rotation. But if I take a point here also, around this point also, I can have a twofold rotation. Similarly, here also I can have a twofold rotation, here also I can have, that is what is essentially is being shown. So once some basic symmetry element is associated with the lattice point, okay, this is only just showing the unit cell. In the unit cell, there are other positions also, different types of symmetry elements are present. These points in crystallography generally they are called as within the unit cell when they are there, they are called as special points. Okay, this is given in the International Union of Crystallography, so one should know, okay. But if I choose here instead of it, suppose I choose a point here and put a axis and try to rotate it by twofold, will I get this one? The pattern will not come identical. That is, only at a point at the lattice point are at the middle of it, that is middle of the x and the y axis. Okay, with respect, only these points where they show the twofold symmetry. Any other point, if I choose an axis, it will not show any symmetry. It will show only one-fold symmetry. That you have to do a 360-degree rotation to come back. These points are generally called as a general point, okay, or these are called as points with no symmetry. Okay. Is this clear? Like here, if you see a rectangular lattice, now we have some mirrors also associated with it. Okay. There are various types of that. This I will come back later about it. But what I wanted to tell you essentially is that consistent with the lattice, there are some symmetry elements which are associated with it. Both are, so twofold essentially is represented by this symbol, twofold rotation. Okay. If it is a fourfold rotation, it is generally represented by a fill square. Okay. Sixfold essentially with a hexagon it is represented. Okay. Threefold will be represented with a triangle. These are all the way. Twofold is essentially represented this way, this rotation axis. Okay. And the mirror generally is represented with a solid thick line. That is what essentially is being shown here. And then this line which is being shown is essentially a glide. Okay. For the purpose of today's lecture, I am not going into a detail of it. Okay. But this I will explain later. Okay. Because today's lecture I just wanted to concentrate only on construction of lattices from 1, 2 to 3. So far what we discussed is essentially from one dimension how two dimension can be constructed. We have seen that there are only 5 types of two dimensional lattices can be constructed. Suppose we have to construct a 3-dimensional lattice, what should we do? Then this periodic lattice which is there, 2-dimensional lattice, we stack them one on top of the other. Okay. Then we can construct a 3-dimensional lattice. But here also when we try to stack them one on top of the other, is there any sum, how many lattices we can construct? Is it infinite? 14 revised lattices are only possible. Okay. You can choose any type of a pattern and do it. This I will, I think the first time when I took the class, I asked all the students to take straw and make it, and they made it, and better than what I expected they could do. I will expect all of you to form into some groups and try to make it. It will be very nice. You will learn a lot than whatever you learn in the class. I can show you a very simple example here. You take this. This is a square lattice. If I put this one on top of it, okay, one on top, and another one on top of it if I put it, this is one. At the middle, another square lattice has been kept. I am just putting an atom which is essentially the same square lattice repeats itself. So this comes on top of it. So this is if it considered as an A type of a lattice, and if it is a A plane and a B stacking, and this will be another A stacking, AB, AB, AB. If you look at this one, A equals B and C will be around root 2 times. Okay. So it is essentially a tetragonal lattice. The same lattice, if I keep one on top of the other, what I do? I create a simple cubic lattice. So depending upon how you keep one on top of the other, various types of lattices which you can, space lattice can be generated. Okay. This is what I want you people to do. This is essentially another one. It is essentially a parallelogram type of arrangement. Here also you can keep one on top of the other and you can generate various types of lattices. Here, if you look at it, this is a hexagonal lattice, correct? In this hexagonal lattice, if I keep it at one particular A position, and this is another position which comes on top of it, the third one which I keep it, if you see 1 A, B and C if I keep it. Now this is also an FCC lattice, cubic lattice, correct. If I keep this in a position instead of it here, if I keep it like this, okay, now this becomes a hexagonal lattice. Okay. These are all only hard sphere model which I had kept it, so they are at a particular ratio. By changing this separation here, okay, if I keep it instead of not touching, keep it like this, A, B, and C if I keep it and another, this becomes a rhombohedral. Okay. Depending upon what the height at which I do it, I can create simple cubic, you can create BCC, you can create FCC, and if I keep this one just on top of each other, it is a simple hexagonal lattice, correct. So, various types of lattices can be made from these two-dimensional lattices by arranging one on top of each other. This arrangement could be, that is, here what I have done it is I have kept on one on top of the other over a symmetry point. I can do it in another way, like here on top of it, if I keep it, it becomes simple cubic. Suppose I shift it little bit like that and do it, what happens? This side face becomes a parallelogram, okay, then it may become a triclinic structure. Okay. Essentially, by arranging two-dimensional lattice one on top of the other, various types of lattices could be generated, and we will just show some sequence which is being shown here. Here it is a hexagonal type of a lattice, A lattice, on top of which a B lattice is kept like what I had shown here, and then a C lattice comes on top of A and B. Okay. That is exactly the sequence. Then on top of which an A lattice will come. Depending upon the height at which these are being kept, okay. If the height is, if the separation between them is S, okay, and the height h is equal to 2s by root 6, it can become an FCC. If the height becomes s by root 6, it becomes a simple cubic. The height equals s by 2 in root 6, then it becomes BCC. If the height h is other than this, it becomes trigonal. If it comes on top of one another, then it becomes hexagonal, okay, and all types of lattices are possible. Similarly, another example is being shown. This is a parallelogram. Okay. This parallelogram which has A not equal to B, okay. I keep another one on top of it, okay, but it is not exactly, if I keep it exactly on top of it at some height, then it will become a monoclinic structure. But with respect to the bottom one, if the top one is shifted a little bit some way, it will create a triclinic structure. Okay. Here in between, if I put one more layer, okay, that is what it creates, a face centered monoclinic, the base centered monoclinic structure comes. That is one face is centered. So, essentially where are we keeping it? Either at a point which has some symmetry associated with it, or a point where there is no symmetry is there. We are trying to keep these two-dimensional lattices on top of each other. Then the total number of lattices, Bravais lattices, which we can generate. Okay. This is essentially showing the structures, but I will just come back. These are all the only 14 Bravais lattices are possible. Okay. Whatever be the infinite number we can try, that is, you have 5 two-dimensional lattices, you can have various way in which you can arrange it. Then you can take the number of combinations which you can try, okay, 5 times whatever the NC you take it, how many, what will be the number. But finally, when we say that only 14 are going to be there, that means that this is also based on some symmetry considerations, correct? So, generally what is being told about these lattices is that these are all based on A equal to B, not equal to C, alpha equals beta equals gamma. That is the way it is being written, right? In most of the books, this is how you might have studied. But it is not based on that, it is based on actually symmetry. In crystallography language, A not equal to B actually means that A necessarily not equal to B. That means that A can be equal to B as well. So, it is the symmetry which says whether it is monoclinic or triclinic or whatever is the structure, and it is not the lattice parameters. That one should always keep it in mind. Okay. That I will come with some example later, how it happens. Okay. So, when we keep this type of two-dimensional lattices, one on top of the other, generally we have seen with respect to either on lattice point or at the middle of it, this will have a fourfold symmetry, we know that. Suppose I keep one on top of the other, and if I look at some other angle also, there may be some other rotational symmetry associated with it. Okay. In a three-dimensional lattice, if I try to look at it, there may be many symmetries which are possible in different directions. If we try to look at all those symmetry elements, okay, then try to look at, then what is going to happen, this is what essentially is being, this is essentially a problem which becomes of a spherical trigonometry. Okay. If we give one rotation in one direction, and in 3 dimensions finally that rotation should be consistent with the translation, so that the pattern should be, the position of the lattice should be, lattice point should become identical with the earlier one. When that is being done, it is like this. If there are axes, we find that in a crystal only two-fold axes are there. That is 3 directions, two-fold axis only, we see nothing else. Then, and each two-fold axis is 180 degree. Then angle between these axes will turn out to be 90 with respect to each other, and that gives rise to an orthorhombic structure. Okay. Similarly, if two-fold axis we find in a crystal, and in another direction we find a 3-fold axis, okay, 3-fold rotation axis, then the crystal turns out to be essentially trigonal. Why am I telling it? Because when you look at the diffraction pattern is the one which you use to find out the crystal structure, right? Then you have to look at symmetry along, suppose I take a diffraction pattern in one direction and diffraction pattern in another direction with respect to some angle, it gives two-fold symmetry. In the third direction, if I take it, if it gives only a 3-fold symmetry, okay. By looking at these 3 diffraction patterns, I can immediately tell that this crystal is a trigonal crystal. You understand that? That is where it is useful. Okay. So, there is some sense to learning all these things. There is a reason for learning all these things. This way, if we consider 2, 2 and 4 gives rise to tetragonal, that if 2-fold, 2-fold and 6-fold is there, it will be hexagonal type of a lattice. 2, 3 and 4, it will be a cubic lattice. Okay. These are all the way it is going to be. 2, 3 and 3, it is going to be again a cubic. Okay. So, in this particular transparency, if you look at it, the classification is based more on the symmetries. Okay. Triclinic, if we take it, a triclinic crystal will have only one-fold rotation. There is nothing else will be there. Crystal structure will not have any other symmetry other than translation. Translational symmetry all lattices will have, correct? Then if you look at monoclinic, okay, monoclinic will have only one two-fold rotation around an axis, and that is the only symmetry element which is present in that. That is the minimum symmetry element which is present. It can have more than that also, but the minimum is, if it is there, then we say that this is monoclinic. If along 3 directions which are perpendicular to each other, if there are two-fold rotation axis is there, only two-fold rotational symmetry, then it is going to be essentially an orthorhombic structure, right? If a crystal has got only one 4-fold rotation and there could be anything else other than that, then that is the tetragonal structure. Suppose a crystal has got only a 6-fold rotation, then it becomes hexagonal. Okay. Suppose a crystal has got only one 3-fold axis rotation, okay, then it becomes a trigonal or rhombohedral. Okay. Suppose we have 4 threefold axes is present, making some angle between them, then it becomes a cubic system. The difference between cubic and trigonal is essentially that in trigonal there is only one threefold axis. Cube we have 4 threefold axes are there. Like for this cube, if we take it, it has along all the 4 body diagonals, there is a threefold axis is there. Suppose I try to stretch it along one body diagonal, then what will happen is that only one threefold axis will be there where we have stretched it. All other threefold axes will vanish. Then it becomes a trigonal structure. Is this clear? Yes.
Is there any correlation between ABC and XYZ?
ABC and
XYZ. Crystallographic
X.
axis. XYZ and ABC.
No, X, Y, Z generally we used to represent the axis. Here ABC represents what are the directions around which these symmetry elements are existing. It could be any, it can coincide with the X, Y, Z, need not also. Like for example, if you take a cubic structure, the threefold rotation, it is being given with respect to B, right? That is essentially along 1 on 1. But the coordinate system which you choose for cubic is along X, Y, Z, okay, it does not match with that. Whereas the fourfold, if you choose it, that will match with one of the, this I will come to explain later, what is the similar, but it need not be the same. Whereas in the case of a orthorhombic structure, the twofold rotation matches with that of the X, Y, Z axis, okay. There is no need for it. Okay. This is essentially what I had given here also. Okay. These are all the various types of, but what is essentially important is that one should remember that all the classification into 7 crystal systems is based on what is the minimum symmetry which it can have. Okay. Then one is that in the case of cubic, we can have primitive, that is simple cubic, body centered, so and then we can have face centered. Okay. These are yes.
Sir, why centered square is not included in the 2D lattice?
Which one?
Centered square. We have centered rectangle, right?
Yeah, centered square. If you take it, it becomes another square.
Centered square becomes
Another smaller square with a by root 2 as the lattice parameter. So its symmetry is square symmetry only. You understand that it's the symmetry which dictates. So essentially all the classification of crystals and crystal structures, lattice structures and all are based on symmetry. What is the type of symmetry which it has got, on that basis we group them. Okay.
triangle.
Eh?
Triangle.
A triangle, if you take it, if you take an isosceles triangle, it is going to be different. It will have only twofold symmetry, it will not have a threefold symmetry. Though we call it as a triangle, symmetry wise, if I join two isosceles triangle, it will become a centered, in 2 dimension, it is a centered rectangle it will become. Correct? That is if I can. Right? This is how it is going to be. But this will have a twofold and not a threefold. Threefold rotational symmetry will be exhibited only by an equilateral triangle. But the same equilateral triangle has got, when we arrange space filling is taking, because the space filling also has to take place with all these tiles. Then when that happens, it will have a hexagonal, that 6-fold symmetry associated with it. Okay. I will come back to the crystal structures later. So what I just wanted to tell is that starting from a 1-dimensional periodic lattice, we can construct only 5 types of 2-dimensional periodic lattice. from these 5 types of 2-dimensional periodic lattice, only 14 types of unique 3-dimensional lattices could be constructed. Okay. Around each of these lattices, either 1 dimension or 2 dimension or 3 dimension, we can put motifs around them satisfying some symmetry conditions, either reflection symmetry or rotation symmetry or a combination of these symmetries. When we do that, that can generate real crystal structures can be generated. That there are some numbers are available, okay, like only 17 2-dimensional space groups can be generated. In 3 dimensions, we can generate only 230 space groups. Those restrictions come. This we will discuss it in the next 1 or 2 classes. Okay. So essentially here, I just today told about construction of lattices from 1 to 2, 2 to 3 dimensions. Is this clear? If you have any questions, please do ask and get it clarified.
So in quasi-crystals, 5-fold symmetry is possible.
Which one?
Quasi-crystals.
Quasi-crystals has got a 5-fold symmetry. Yes. Yeah. Essentially, quasi-crystal is not a periodic lattice. Many of the material in nature show a 5-fold symmetry which is there. Okay. When we talk about point group symmetry, I will tell you what it is going to be. It can have 2m, mirror symmetry is possible in quasi-crystals, 2-fold symmetry is possible, 5-fold symmetry is possible. That is the combination which it will show. Because so far when we talked about here a tiling which is with respect to a tiling which fills the complete space, correct? If we do a tiling model, quasi-crystal essentially is a particular type of which is a 5-fold symmetry, correct? In that tiling, if I put one quasi-crystal, this one regular pentagon, and keep another on top close to each other, there will be some gaps which will be there. That will be essentially rhombuses which will come. So generally this filling is called as a fat rhombus and a lean rhombus, because the angle between them will be different. That is 2 types of, one rhombus can be like this, another rhombus can be thin type, specific arrangement of which these tiles fill the lattice. Okay. Earlier it was thought that the periodic arrangement is with respect to translational periodicity, because quasi-crystals does not have a translational periodicity, but it has a symmetry. 5-fold symmetry is possible, but periodicity is not possible. You understand that? That is the basic difference between these 2 structures. But generally when we talk of periodicity, we talk with respect to 1 dimension, 2 dimension and 3 dimension, correct? The one which appears as a 2 dimension which is periodic, if I look at it, we talked about a reflection, right, with respect to a plane mirror. Suppose I take a concave mirror and look at it. In that space, how will it look like? It will look distorted, no? It will not have the periodicity. So when you go to higher dimensions, depending upon which space we are looking at it. When we are looking at a normal Euclidean space, this is how the periodicity is defined. When we look into other space, similarly, the structure which does not show any periodicity, that is, if we look through a curved mirror, you will see that it looks as periodic, but in reality it does not have a periodicity. So essentially all these periodicity which we look mathematically, when you try to define it, it is with respect to some frame of reference which we choose it. Depending upon that, there are going to be changes. Okay. That is why when diffraction pattern in quasi-crystals people try to interpret it, which I will towards the end I will come to. Okay. Then they thought that only in the 5th dimension or 6th dimension you can have periodicity. Okay. That is the way it has been worked out. So what is periodic or not periodic in, because normally we are able to visualize it only in a dimension which is up to 3. But mathematically we can define any dimension, we can attach to it, right? And such a way when we try to process it, we find that I think it's in 6 dimensions or 5 dimensions. It's being looked at. Okay, we will stop it here.